Good day, students. Welcome to part two of our application of derivatives. We're working on optimization. And the kind of optimization problem we're going to be dealing with in this clip is optimizing the volume of an enclosure, okay? Actually, this is going to be an enclosure done using a wireframe. All right, so let's take a look at the question. All right, so a designer wants to build the frame of a rectangular box with a square base using a wire that is 60 meters long. What must the dimensions of the rectangular box be in order for the volume enclosed by the wireframe to be maximized? Okay, so let me give you a sketch. Let's consider a sketch of the situation. All right, so there goes a depiction of the situation we're considering. We have a box built out of this wire. Okay, so basically you just cut up this wire and you just create the wireframe of this box. All right. So the constraints are as follows. The base of this construction we have just made is a square. Okay, so it says it has a square base. All right, so let's call the dimensions of the base x and x. Okay, because it is a square. All right, so if this is x and this is x and it's a square base, then we know that the entire base is going to be x, x, x. And since it's a box, we know that the two parallel faces are congruent, so this would also be x, 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 and x. Okay? All right, so this is just, I just constructed this using the idea that the base is a square. All right, so let's see if we can figure out what the height of this rectangular box is. Okay, so this is the entire segment right here. So let's say the entire segment is 60 meters long. So this entire segment from here to here is 60 meters long. And what have we done now? We have taken some portion out of this entire length, okay? We've taken the wire that's used to construct the base and the top, the bottom and the top of the rectangle, okay? So we had 4x's on the bottom. So for the bottom, we have 4x's. All right, so let's take that out. This is the first 4x for the bottom. And then for the top of the wireframe, we took out another 4x's. Okay, so take out another 4x's. All right. All right, now what do we have left to construct the uh, the vertical components or the vertical bars of this box? Okay, so how much length do we have? In order to figure that out, all we just simply do is we subtract 16 from the combination of these two. All right, these two combine together to give you 8x. So what you have left to create the vertical beams or the vertical frames of your box is 16 minus 8x. Okay, the entire length minus the length that you use to construct the top and the bottom. Okay, so how many vertical beams do we need? We need 1, 2, 3, 4. We need 4 of them to construct our box to connect the top and the bottom. All right, so how does that relate to what we're doing here? Well, since 60 minus 8x is a combination of all 4, what would the length of each one be? So let's break this further into 4 parts. What would the length of each part be? It's simply going to be the whole thing divided by what? Divided by 4. Right? 60 minus 8x divided by 4 will be the measure of each segment. Okay? All right, so let's just keep that in mind. Now, before we go back to solving the problem, let's strategize real quick. So in this problem, we're optimizing or maximizing volume. All right. So how do we approach this? Well, whenever we're optimizing volume, what we want to do is we want to express the volume in terms of just one variable. Okay. So v of x, v in terms of, let's say, x is a function in terms of just one variable. And then if we can get ourselves to express the volume in terms of one variable, then we can find the critical points, which we can get by differentiating the volume function. And also, when we define the volume function, we also have to know the constraints on our independent variables. So for some a less than or equal to x and less than or equal to b. Okay, that would be the boundaries on our volume function. And then what we'll do is we'll basically differentiate the volume and set it to 0. That will help us find the C or C's critical values. Okay. So what we now do is after differentiating this volume and setting it equal to 0 and finding a critical value, we'll just test the upper, lower bound, and the critical values. So we're going to test, we'll test V of A, the lower bound, V of B, the upper bound, and V of the critical values. No matter how, considering how many they are, we'll just plug them into the original function. And whichever one is the biggest, that is the side length that will yield the maximum volume. All right, so that's the whole idea here. Okay, so let's go back to this problem. In this problem, we can reduce this portion 16 minus 8x over 4. Actually, that's for each segment, so let's not get this confused. So each segment is going to be that measure. All right, so if I wanted to figure out, let's say, what this one tiny piece here is going to be, that's going to be 16 minus 8x over 4. And if I reduce that, it's going to be 4 minus 2x. Okay, so guess what? This side line right here, from here to here, let me project it down. From here to here is 4 minus 2x. And then here also is 4 minus 2x. This is 4 minus 2x. And here is 4 minus 2x. Okay, what is the significance of that? Well, that's the vertical component of our rectangular box, right? So this side length right here is 4 minus 2x. And this is 4 minus 2x. The back there is 4 minus 2x. And then the front right here is 4 minus 2x. And if you add everything together, you're going to end up with 16. Okay, so let's see. Now to do this, well, we also have to know what x is. So in order for us to do this, we are going to have to use the area, the formula for the volume of a cube. Okay, the volume of a rectangular prism, not a cube. So the volume of a rectangular prism, V, is basically the area of the base, length times width times the height. Okay, that's the formula for area of a rectangular prism. That's the case we're dealing with here. We know that the square is a special case of a rectangle, so this is the formula we're using. Okay, so we know that the length, let's call this L, and call this W, and call this H. So the length is x, and the width is x because we have a square base, and the height is going to be 4 minus 2x. Okay, so that's going to give us the volume formula. V of x equals length times width times height is going to be x times 4 minus 2x. Okay, you see the beauty of this formula? The beauty of this formula resides in the fact that you have only one variable, and that's always the goal. You always want to express whatever formula you're optimizing in terms of just one variable so you can differentiate with ease. Okay, so that's the case here. So simplifying further, v of x is equal to, if you distribute everything out, you're going to have 4x squared minus 8x cubed. Okay, now what are the constraints on x? Well, if we wanted to make the rectangular base as small as possible, basically allocating all our resources to just the perpendicular, the vertical beams, or the vertical edges, then there will be nothing left for x. X will be really, really small. So the lower limit for x is 0. X can be as small as 0. And x can be, how big can x be? Well, what if we wanted to allocate all our wire to just constructing the top and the bottom? Okay, what would the dimensions of x be? Well, in order for that to happen, all we just be left with is the top and the bottom, right? So if we devote all our material, all the wire to just the top and the bottom, the question is what are the dimensions of x going to be? Okay, so if we're devoting all our material to just the top and the bottom, we know that the top and the bottom are both going to be squares, right? So if we have a square on the bottom and a square on the top, we're going to have 4x on the bottom for the bottom part, and then plus 4x on the top. Okay, we have nothing else allocated to the vertical beams or the vertical frames Everything is just top and bottom because we want to make it as x as big as possible, so x consumes everything, okay? So all we have material for is just the bottom and the top, and it has to be a square, so we have 4x's on the bottom and 4x on the top, and that has to add up to all the length, all the material we have, which is 16, okay? So that gives us 8x equals 16, divide with size by 8, and they have x equals 2, okay? So guess what? This is the biggest that x can be, all right? That's your upper limit. All right, so x goes from 0 all the way to 2. Is 0 when you allocate all your wire to just creating the vertical beams and you have no base, okay? And 2 is when you allocate all your resources to just doing the top and the bottom and you have no vertical beams, okay? All right, so there goes the boundaries for our x. Now, we need to find our critical values so we can test the endpoints and the critical values to see which yields the biggest volume, and that will be our answer, okay? All right, so to find the critical values, we need to differentiate this volume function. So v prime of x is going to be, using the power rule here, we'll have 8x. And then differentiating this using the power rule, we'll have 16. Okay, I just ruined my entire formula. Quick correction. This is supposed to be 2 right there. So this is 2. Okay, and then when I differentiate this, it becomes uh, 3 times 2, 6, 6x squared. Okay, sorry about that. Because when you multiply x times 4, you have 4x squared. X times 2x, you have 2x to the third. I don't know where 8 came from. Anyway, so this is it. All right, so now we have our differentiated function. So this is what we're going to be setting to 0 to find the critical values. All right, so what we're going to do here is we're going to set, like we talked about before, v prime to 0, 8x minus 6x squared equals 0. So we have a quadratic equation here. We can factor it out, factor and solve. So I can factor out 2x. So if I factor out 2x, I'll have 4 minus 3x equals 0. And then using the zero product property, we can set 2x to 0 or 4 minus 3x to 0. In this case, x is equal to 0. And if you solve this, you add 4. Subtract 4 and divide by -3, you have x equals 4/3. Okay? All right, so now we have our critical values and the endpoints. This overlaps with that, so we just have to check 0 once, and then this is in between, and that's the maximum. All right, so which will yield, which of these candidates, 0, 4/3, or 2, will yield the biggest volume? That's the question. All right, let's go ahead and test them out. Start with v of 0. V of 0, we're going to be plugging these values into the original function here. Okay, this is what we're plugging it into. So v of 0 is 4 times 0 squared minus 2 times 0 to the third. All right, so that gives us 0 minus 0, which is 0. That makes sense, right? Because if you devote all your resources to just making the height, you cannot enclose any volume, okay, because you don't have any base. You just have length. Height, I mean. All right, so v of 0 is 0. All right, let's try the upper limit, which is v of 2. In this case, we're allocating all our resources to the top and bottom and nothing to the height. Let's see what happens here. So we have 4 times 2 square minus 2 times 2 to the third. Okay? 2 square is 4. 4 times 4 is 16. Minus 2 to the third is 8. 8 times 2 is 16 equals 0. Okay? This makes sense too, right? Because if you devote all your material to just making the top and the bottom and no material to the height, your rectangle will have no depth. It will just be a flat surface and it will hold 0 area. It will enclose 0 area. So you can see that the upper and lower limits of x both yield 0. Okay? So that means that this has to be the answer, right? V of 4/3. So let's go ahead and plug that in and see what we get. So plug that in, we have 4 times 4/3 square minus 2 times 4/3 to the third. Okay? If you work this out, you end up with 64 over 27 cubic meters. All right? So this is clearly bigger than the other two. The other two extremes basically hold no area at all. All right, so we basically know what the dimensions of the base is, right? We know that L is going to be 4/3 and the width is going to be 4/3, right? Because we indicated earlier that the base is a square and L and W are both x's, okay? But we need to find h. What on earth is h? H, we found out earlier, was 4 minus 2x in its reduced form, right? Well, x is 4/3, so let's put that in there. So 4 minus 2 times 4/3 will help us figure out the value of h. So we're going to have 4 minus 8 over 3, which equals 12 minus 12 over 3 minus 8 over 3. And then when you do the fraction and you work this out, you end up with 4/3. Okay? So the length is 4/3, the width is 4/3, and guess what? The height is 4/3. Okay? So there goes your answer. So take a look at this answer for a minute. What does that tell you? What kind of shape is this? It tells you that you're actually creating a cube. All right? So the cube is actually the shape that creates the biggest volume, that optimizes the volume. Okay? So there you have it. So thanks so much for taking the time to watch this video. Feel free to subscribe to my channel so you can get updates on other cool clips such as this. If you like this video, you can click a like down here. And please, please, please post a comment. Tell me what you think about this clip. More videos can be found on mycoachserve.com. Thanks again and have a wonderful day.